Welcome back. So it's now time to actually define what uniform convergence is. So let's say that we have a sequence of functions fn, and these functions are all defined over some domain D. And let's say that this sequence of functions is a convergent sequence of functions, and it has pointwise limit, this limit function f here. We say that it obeys this stronger notion of convergence, uniform convergence, if it obeys the following condition, that for all epsilon greater than 0, there must exist a big N as an element of the natural numbers, so a term in the sequence of functions, such that, and this is the important bit, for all x is an element of your domain, if you go to a term in the sequence beyond big N, so if little n is greater than or equal to big N, and you go to any one of these points in the domain and you look at how far away this term fn at x is from the limit evaluated at x, that it is less than epsilon. So the crucial thing here is we are now insisting that whatever epsilon you give, that there must be one big N that works for all x in your domain, not them all having separate different big N's potentially and converging at different rates. We want one big N that satisfies this condition for every point on the domain. That is this notion of uniform convergence, and as you can see, it's a stronger version than what we had previously with the pointwise convergence. Now there is a lovely intuitive way of visualizing this, and that's what I'm going to show you now. So again, here is our domain for our functions. And in red, this is supposed to represent the limit, and we're now supposing that it's going to be a uniform limit. That's the name for the limit when the sequence of functions converges uniformly to it. We can call it a uniform limit, which is stronger than just being a pointwise limit. So this in red, we're supposing is now our uniform limit. And what you can now do is for each epsilon, you can imagine drawing an epsilon interval around your function. So that's what I've done in blue here. So I've gone above the function by epsilon at every single point in your domain. So here I've gone above by epsilon and I've gone below by epsilon. So I've drawn a little epsilon interval around it. And then you can continue this for all the points of your domain so that you get this sort of picture like a tube containing your uniform limit in the middle here. And then what this is saying is that if you look at the sequence of functions, which I haven't drawn on this picture because I don't want to clutter it up, so I've put them here, then there must exist some big N, so a term in this sequence of functions, such that for all the points in the domain, if you go to that term of the sequence and beyond it, they are all inside this tube here. So if you go to any point on the domain, the difference between the function in the sequence and the uniform limit must be less than epsilon. So what that does correspond to is that from this point onwards in the sequence, if you drew them on this picture, they would be contained within this tube around your uniform limit. So none of them would step outside of this. They'd all be inside here. So that's the intuitive way that you can view this stronger uniform notion of convergence, that for all epsilon greater than 0, so however small, however narrow you want to make this blue tube here, you can make it, these blue lines, as indefinitely close to the red line as you like by making this epsilon smaller and smaller. There must exist a term in the sequence of functions such that it and all the terms beyond it are contained in this blue tube around your uniform limit entirely over their entire domain. And I hope you understand why this is called uniform convergence. It's because in some sense it means that at every point in the domain, the sequence of functions is converging to the limit at the same rate. Now, of course, at different points in the domain, the convergence might be at slightly different rates, but it's not too much. So if I go back to my example to illustrate what I mean by this, we looked at those 2 points, 0.9 and 0.01, and I've erased the workings now, but those I remember were the 2 points we looked at. And we saw that one required a big N of 11 and the other required a big N of over 900, 901 I think it was. Now you might say, but surely I could make big N equal to 901 and then it would work for both of them. You could. then it would work for those 2 points. The problem with this example is that by making x smaller and smaller and smaller, if I take an x that's even smaller than 0.01, say I go for 0.0000001, then the big N needed for that will be even bigger than 901, much, much bigger than 901. And in fact, by getting closer and closer to 0, I can get an indefinitely big N that is required. And that's the problem, that in this example, the big N's are too far apart. There's too much non-uniformity in the way that they're converging. It's unboundedly different, the rates at which they're converging over this domain. Whereas if the sequence of functions converges uniformly, they must be converging enough, they must be converging similarly enough that it's not unbounded, that there must be some big N that works for every single point in the domain. Whereas in this example there isn't, because of the fact that as you get closer and closer to 0, the big N that is required will get bigger and bigger and bigger, and it won't be bounded above how big it has to get as you get closer and closer to 0. So what I now want to do is formally show you that this sequence of functions that converges pointwise to this limit does not converge uniformly to this. So this is the pointwise limit for this sequence of functions, but it is not a uniform limit. It does not obey this heightened criteria. And intuitively, here's the picture for why this isn't going to happen. So I've plotted on my pointwise limit here. So it's 1 at 0, and then everywhere else on the domain from 0 to 1, it is 0. And now I'm going to take as my epsilon here a half, and I'm going to show you how even for epsilon is equal to a half, this cannot be fulfilled, and therefore, given that we need it to hold true for all epsilon greater than 0, and it doesn't hold true for epsilon is equal to a half, this criterion cannot be met. So what I'm now doing is drawing like my tube around my limit here. So here is a half, and I've put the upper bound of this open interval above my 0 here. And then at 1, of course, it's not really a tube, it's just an interval, because there's only 1 point there. So this is 1 plus a half, and this is 1 minus a half, i.e. a half. And intuitively, the reason that this isn't going to hold true is that if I take any one of these functions, there's always going to be a little bit that's close to 0 that isn't in this tube around the limit here, because as soon as you go forward from 0 to anything that's greater than 0, instantly the function now has to be in this part of the tube here. It only has to be up here at that one single point, which is 0, but everything else it instantly has to be down here, and you can see that that's not going to happen. These functions are all continuous, so for a tiny little bit, even at really, really big N's, they're still going to be above this line, i.e. not within the required tube around your limit here. So I've moved the board for some more space, and I've copied some of the essential information that we need. So here, of course, is our sequence of functions. Fnx is equal to 1 over 1 plus nx. And we are going to show that this doesn't converge uniformly to its limit, shown in red here. And we're going to show that it doesn't even obey this for epsilon is equal to a half. Now, we've drawn on the epsilon is equal to a half tube, if you like, around the limit in blue here. And the point that we are not going to be interested in is x is equal to 0, because actually every single one of these functions obeys the criterion of being inside the blue tube at x is equal to 0, because all of them are equal to 1 at x is equal to 0, which of course is the centerpiece of the tube. So they're all going to obey it at x is equal to 0. So we're not interested in that bit. We're interested in what happens very close to 0 in this positive part of the domain here. So we're interested in this part of the domain from open 0 to closed 1. And on this part of the domain, if this criterion was going to be obeyed for epsilon is equal to half, it would have to be true that the modulus of the difference of the function from the limit, which is 0 everywhere, would have to be less than a half. And we are trying to find a range of n values for which this is true for all x. And what I am going to show you is that no such range exists. In fact, for every single n you take in the natural numbers, there are some x's for which this does not hold true, and therefore there cannot be any n's such that for all x's in that domain this holds true. So I've simplified this a little bit. I've got rid of the minus 0 because that doesn't have any effect, and then I've got rid of the absolute value signs because this is a positive number anyway. So we are actually trying to find n values such that 1 over 1 plus nx is less than a half for all x in this domain. Now, to help with this, I've just drawn the picture on here for one of these functions. It looks something like this, coming down from 1 and then going down to something small. And then as you make n bigger and bigger, they become steeper and steeper and steeper. And what I am now trying to say is that I'm trying to find n values such that the moment you get past 0, the moment you step into the actual positive real numbers, this is instantly true, that it's instantly less than half, i.e. within this blue tube around my limit here. And of course that's not going to be true because some of them, these are continuous functions, they have to be above there for a little bit. So I'm now just going to show you that for each one of these functions, I'm going to find that little interval of positive real numbers where they have to be greater than a half. And I'll do that for each n, and therefore I'll show you that every single one of these functions has a little interval that doesn't obey this. So imagine we've picked an n then, so we are looking for the point where this function is greater than or equal to a half. So 1 over 1 plus nx must be greater than or equal to a half. Just rearranging this inequality, 2 is positive, 1 plus nx is also positive because n is a positive natural number, x also, we're only interested in positive x values, so we can rearrange this to 2 is greater than or equal to 1 plus nx. And then subtract 1 from both sides and we get that nx must be less than or equal to 1, and then dividing through by m because it's a positive natural number, we get that x therefore is less than or equal to 1 over n. So what I have found from that is if you take any one of these functions in the sequence, fn of x, on the interval from 0 to 1 over n inclusive, it is going to have a value greater than or equal to a half. So I have found this little interval here that is above that blue line, that is not obeying this uniform criterion. It's not within that tube of the limit. And for all n in this sequence of functions, every single one of these functions, no matter how big n you make, there's always going to be this tiny interval. Yes, it's getting smaller and smaller as n gets bigger and bigger because 1 over n is going to get smaller and smaller, but there's always still going to be that tiny bit of interval where the value of the function on that interval is greater than or equal to a half, and therefore you cannot possibly find any point in this sequence where for that term and all terms onwards, this inequality holds true, i.e. that the function, as soon as you go beyond 0, is within this blue tube of the limit 0. So it does not possibly obey the uniform convergence criterion, even for this quite big epsilon is equal to a half. So even though this sequence of functions does converge pointwise to this limit, it does not meet the heightened criteria to be said to converge uniformly to this limit. So before we finish, I would just like to give you an example of a sequence of functions that does converge uniformly. This is a very simple example, but it will illustrate the point. So the sequence of functions I'm going to take is going to be fn of x is equal to 1 over n sine of x, and the domain here is going to be the entire real line. So firstly, let's find its pointwise limit. So I've drawn a picture here, so in black these are representing 2 of the functions in this sequence. So if you like, this one that I'm tracing at the moment is the first one, so 1 over 1 sine of x, which is just sine of x. And then as you go forward to the second one, we'll have a half sine of x, so that will look very similar, but of course the peaks and the troughs will all be at half modulus, so we'll only get up to a half here rather than 1, and we'll only get down to minus a half rather than minus 1, and it will continue on like that. And then for 3 it will get even smaller size, so you'll have now a third sine of x, so we'll just get up to a third here, and minus a third down here, a third, minus a third, and then you can see as you go on, the modulus, the extremes, the peaks and the troughs of the sinusoidal wave are just going to get less high or less low, and they're just going to be converging it in. So hopefully you can see intuitively that the function that this is going to be converging to is just the zero function for the entire real line. But let's just think through it pointwise. So now what we do is imagine fixing x. So we've taken a specific point here, and now we've got a sequence of real numbers now, and we think about the limit of that. So we've got the limit as n approaches infinity of 1 over n sine of x. Sine of x is just a constant between -1 and 1, depending on what x you pick. And this sequence, of course, goes to 0 because a constant times the sequence 1 over n still goes to 0 as n goes to infinity. So this is equal to 0 no matter what x you pick, because sine of x is always bounded no matter what x you pick. So this sequence of functions converges pointwise to the 0 function. Let's now try and ask, does it converge uniformly to that 0 function? And you can probably appreciate that yes it does, because if we draw our limit with the tube, so here is our limit, which is the 0 function, and then I've taken some epsilon and I've drawn this epsilon interval around the limit all the way along, and then it needs to be the case that in my sequence of functions, at some point and for all terms beyond it, they are all inside this blue interval drawn around my limit function. And you can see that these sinusoidal functions, they're getting, as n gets bigger and bigger, their peaks and troughs get smaller and smaller, so they will at some point be contained inside this tube, as long as you make their peaks and troughs contained within this blue tube, which you can do by making n bigger and bigger. Writing this out formally, so I need to take any epsilon greater than 0, so let epsilon be greater than 0. What I need to do is find a big N now, such that for all x is an element of the real line, if little n is greater than or equal to big N, then if you look at the modulus of the function fn of x, which is 1 over n sine of x, and you take away the value of the limit, which is 0 everywhere, then that is less than epsilon. Simplifying that, I can get rid of the minus 0, and then I've just got mod of 1 over n sine of x needs to be less than epsilon, and I can split that into mod of 1 over n times the mod of sine of x. Now, 1 over n is a positive number because n is a positive natural number, so we can get rid of the absolute value signs around that. We can't get rid of the absolute value signs around sine of x because for some x values, sine of x will be a negative number, so they need to stay there. So this is what we need to do. We need to find a range of n values such that we can find a big N at the bottom of that range of n values, such that for all x in the real line, this inequality holds true for your given epsilon. Now what we do is just play the normal game of inequalities that we play in analysis. So we notice that whatever x you take in the real line, 1 over n times mod of sine of x is always going to be less than or equal to 1 over n. The reason being is that the function sine of x for all x in the real line is always between -1 and 1. Therefore, mod of sine of x is always between 0 and 1. So the maximum value this can take is 1. Other than that, it will be between 0 and 1, i.e. something less than 1. So if you imagine it's 0.5, of course you're going to end up then with something less than 1 over n. You'll end up with a half 1 over n. If it's equal to 1, then you'll end up with 1 over n exactly, but the biggest thing it can possibly be equal to is 1 over n, this product here. So we always know that this is true. 1 over n times mod of sine of x is going to be less than or equal to 1 over n, no matter what x is an element of the real line you pick. So if you then make 1 over n less than your epsilon, then you are guaranteed that this inequality is true by transitivity, because if this is less than or equal to this, and this is less than epsilon, then you can conclude that this is less than epsilon. So all you now need to do is make sure that this inequality is true, that 1 over n is less than epsilon, so you pick an n such that this satisfies this. So just rearranging that, you get that little n needs to be greater than 1 over epsilon. So we now have our range of little n values such that this inequality will hold true. So all you now need to do is take a big N that is greater than 1 over epsilon, and then if you take any little n that is greater than or equal to big N, they will also therefore by transitivity be greater than 1 over epsilon, and hence this inequality will be true. So to summarise the argument then now, let epsilon be greater than 0, take as your big N something that is greater than 1 over epsilon, which by the Archimedean property there will always be a natural number that is greater than 1 over epsilon. And then, if you take any little n that is greater than or equal to big N, then by transitivity little n must also be greater than 1 over epsilon, because it's greater than or equal to big N, which is greater than 1 over epsilon. And then you can rearrange that to 1 over n is therefore less than epsilon. And from that, you can get that 1 over n times mod of sine of x for any x is a real number is also going to be less than epsilon, because it itself is less than or equal to 1 over n, and 1 over n is less than epsilon. And this is precisely what you need to be true in order for the distance from the function at any real number to be less than, from the function to the limit, to be less than epsilon. So that completes that example of a sequence of functions that converges uniformly to its limit. With that, we will finish the video here. Thank you for watching.